Terus saya panggil Mas Yoga.
Oke. Nah, good evening, Prof. Mr. Rames, Profesor
Halo,
Rames. Halo, halo.
semua?
Apa kabar? Apa kabar semuanya? Waduh, ketemu di online nih sekarang.
Ya, semua. Pak Iwan,
Ya,
apa kabar?
Ya,
ya,
Pak Rames, thank you
Ya,
ya,
for attending here.
ya. Bu
Kita menunggu ini ya,
Bu Aziza, ya.
menunggu Profesor itu ya, Pak Prof. Speaker.
Izam belum masuk lagi ya.
Ya, tunggu. Izam.
Ya, Prof. Izam baru masuk nih.
Prof. Izam sedang coba masuk.
Sudah masuk, sudah masuk.
Oh, sudah masuk. Oke, oke.
Oke. Oke, kita bisa. Halo, selamat malam, Prof. Izam. Good evening.
Good evening, Prof. Rames,
selamat
Prof. Izam, and Madam Nur Aziza ya.
Halo, Assalamualaikum.
Waalaikumsalam.
Waalaikumsalam warahmatullahi wabarakatuh. Bu Ginas, silakan dibuka saja. Udah kumpul ya, Pak Adri?
Ya, ayo, Dok.
Ya,
Oke.
silakan, Bu.
Oke, can we start, Pak?
Ya, oke, right.
Oke, Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Waalaikumsalam.
Good evening, everyone. Thank you so much for being here. It is my pleasure to welcome you to International Guest Lecture ITPLN in collaboration with Unit 10 Malaysia in the subject of Electrical Power System Analysis. Yang saya hormati Profesor Dr. Rames Singh, Deputy Vice Chancellor Academic and International Unit 10. Yang saya hormati Mr. Iwan Tutuka Pambudi, MN PhD, the Vice Rector for Academic Affairs ITPLN. Yang saya hormati Dr. Insinyur Dami Johar Damiri, MSI, Dean of the Faculty of Electricity and Renewable Energy ITPLN. Yang saya hormati Mr. Adli Senen, STMT, Vice Dean of the Faculty of Electricity and Renewable Energy ITPLN. Yang saya hormati Profesor Dr. Izam Zainal Abidin from Unit 10 as the guest lecturer who will share the class material tonight. Terima kasih Prof karena meluangkan masa Anda malam ini. Yang saya hormati dear fellow lecturer from ITPLN and Unit 10 and all of my students from the subject. Let me introduce myself. My name is Ginas Alfianingsi. I am lecturer in ITPLN, especially in the Faculty of Electricity and Renewable Energy, and I will be your MC and moderator tonight. Okay, for the information, it is the first international guest lecture for ITPLN. Terima kasih untuk Unit 10. This week there will be 9 subjects that will have a guest lecture from Unit 10 for 3 study programs in ITPLN: Electrical Engineering Program, Electrical Power System Engineering Program, and Electrical Technology Diploma Program. And tonight is our very first meeting for the subject of Electrical Power System Analysis. So, Prof. Izam and team, maybe there will be tens of students joining this meeting, consists of regular student and the employee student. which most of the employee student is the employee of PLN, Indonesian Electrical Provider Company. Okay, before going any further, let's begin this class with welcoming speech from Mr. Iwan Tutuka Pambudi, MN PhD, the Vice Rector for Academic Affairs ITPLN. Mr. Iwan, the floor is yours.
Okay, thank you very much, Ibu Ginas. Tonight I'm very happy, because our best friend from Unit 10 attending here. Okay, good evening, ladies and gentlemen. Thank you for being present in tonight's lecture, and special thanks to Prof. Izam for agreeing to be guest speaker on the subject of electrical power system analysis. And also many thanks for our special friends, Prof. Rames and Prof. Nuraziza. As we all know, ITPNN and UNITEN are currently establishing a collaboration for student visits, student exchange program, faculty exchange program, guest lectures, research collaboration, joint degree program, and more. ITPLN has also undergone an audit by UNITEN based on the MIRA standard, the Malaysia Research Assessment, and achieved a rating of 2 stars out of a maximum of 6 stars. Our next target is to achieve 4 star, hopefully within the next 2 years. And ITPLN will also send several students to UNITEN for approximately 2 weeks to visit UNITEN, so that ITPN students can get to know the UNITEN campus better. Hopefully, this program can be implemented soon. And also last week, UNITEN signed a Memorandum of Understanding, or MOU. Prof. Rames was here with PLN and for the purpose of capacity building. Okay, once again, thanks you, and may we all succeed together. Thank you. Please, Ibu Ginas.
Okay, thank you, Mr. Iwan, for your welcome. The next agenda is welcoming speech from Professor Dr. Ramesh Singh, Deputy Vice Chancellor Academic and International UNITEN. Good evening, Prof. Ramesh.
Good
The
evening.
floor is yours.
Okey, terima kasih Ibu Ginas. Good evening, Pak Iwan, Vice Rector for Academic Affairs, my colleague Prof. Izam, Dean of College of Engineering, Prof. Adri, Dean of Faculty of Electricity and Renewable Energy, Management of ITPLN, respected colleagues from ITPLN and UNITEN, and students. I'm very happy to be invited to say a few words in this guest lectures partnership at ITPLN. It is an honor for UNITEN to be part of the ITPLN guest lectures partnership. I was made aware that there will be a total of 12 guest lectures covering various topics in electrical power systems, which will be delivered by UNITEN staff to students at ITPLN. These guest lectures provide an opportunity for students to learn from UNITEN experts in their respected fields as they bring a wealth of knowledge and experience, thus offering unique insights to latest technology, industry practices, and future trends that may not be covered in regular coursework or classroom. It also provides an excellent opportunity for students from ITPLN to interact, learn, and network with our academic staff. The guest lectures delivered by external speakers from different backgrounds and experience would also expose students to diverse perspectives and ideas about the topic. In this case, it is related to electrical power systems. This can broaden their horizons, challenge their assumptions, and foster a more inclusive learning environment. Exposure to diverse viewpoints encourages critical thinking and promotes a well-rounded education. Finally, I'd like to thank the top management of ITPLN for having Unit 10 as part of your guest lectures, as I strongly believe that such initiatives would enrich the educational experience of students. As Pak Iwan mentioned just now, we have signed MOU recently with PLN and also with ITPLN. We hope, Unit 10 hope to be a strong partner for ITPLN, and we will support where possible to assist ITPLN to achieve the world-class status. To our academic staff involved in the lectures, thank you for your support in making this collaboration a great success. To students, have a great learning experience. Terima kasih dan salam hormat. Thank you.
Thank you, Prof. Ramesh, for the welcome and insight. Before we start, I want to say hello to Madam Nur Aziza. Good evening, Madam. Thank you for arranging this course. Okay, so for our student, I will tell you about this course mechanism. Maybe you have known that the topic is economical operation in power system. We will learn about load curve and characteristic, primary and secondary loads, and power plant until the operation settings. In the chat room, I just put the virtual background so you can download it and use it among this course. So don't forget to activate your camera. And the students must turn off the microphone, and it can be activated later during the Q&A session, or you can type your question in the chat room. Okay. In the end of the course, the student must fill out the attendance form. The link will be given through the chat room in the end of the course. For our student, is there any question about the course mechanism before we start? Okay.
No, thank you.
Okay. Actually, we can talk in Bahasa or English or Melayu, yeah. Okay. Is there any question? No?
Enough.
Okay. Okay, ladies and gentlemen, let's go straight to the main agenda. For the student, maybe you all have studied about load flow analysis. You have learned about the voltage and phase analysis of every types of bus in the power system. Tonight, you will study further about that, about the setting operation. Would you please welcome Professor Dr. Izam Zainal Abidin to share the class material. Good evening, Prof. Izam.
Good evening. Thank you. Thank you for inviting me to come. Can you hear me okay?
Yes, it's very
All right.
clearly. Thanks for being here,
Okay.
Prof. I'm sorry for the time we held the course in the evening because there are many students from employee program, Prof.
No problem. No problem. Let me share my slides first. Just a minute, yeah.
Yes.
Okay. Can you see me okay?
Yes.
Can you see the slides?
Okay. It's
Yes.
okay.
All right.
Okay, so please, Prof, the time is yours.
Okay. Thank you very much. Let me switch on my laser pointer. Okay. So thank you for inviting. So today, as what's explained just now, I will cover the topics. In general, I hope I covered the right element that is required. If not, I will add on a bit more. So we will cover on power systems, loads, generations, and operation. Okay. Okay. So I would just like to get some brief background. So the students here have actually covered basic power systems, or maybe just a basic. What I meant is, have you covered basic power system as in the main building blocks of power systems, or haven't? If I may get some feedback from the audience.
Feedback from the students, please.
Very clear.
Okay, it's okay. So what I plan to cover would be these three main elements that covers about. I do a bit of a recap on what is power system network is all about, some load type, load profiling, and maybe some basic elements of power system dispatch, and how things are related to
I'm sorry, Prof. Izam. I think your voice is mute.
Yeah.
Has been mute.
Can you
Okay.
hear me again?
Okay.
Okay. Yes. Thank you.
Okay, all right. Okay, let me repeat that again. So basically, I'm covering the power system network. I will do a quick recap on what is power system network and what it consists of, and the different types of generations, and different types of distribution and distribution loads. And then from there, I will zoom in more towards load profile, what load is all about, what are the elements that we looked into load, and also how it relates back to power system dispatch. And in terms of generation, I will also cover on different types of generation, the main type of generators, and some examples of distributed generation. Then I will try to wrap up to cover the topic related to how do we actually manage the power system network, and in general, what will be the guidelines that are required for this to happen. Okay. All right. So just a quick recap on the power system network. As you can see here, the power system network covers three main areas, which is the generation. I think everybody knows the generation covers where the energy is being supplied to the network. And when energy is supplied from the network, it has to be transmitted, in this case, across transmission lines. It can be short transmission line, it can be long transmission line, and basically it has to go through substations. And then from there, it goes through a distribution system network that consists of various types of network load type. In this particular case that you see here, it covers industrial loads, commercial loads, residential loads, and maybe transportation, depending on the type of loads that you have connected to your distribution network. Okay. So a quick recap on generation. Okay, so the main function of generation is to ensure that there is an energy source injected to the grid, and this is particularly very important because for a network to actually function, you must have an energy source to be injected so that your load can actually receive the required energy that is being dispatched to the particular load. So in general, just to recap, generation converts what you have as an natural resources of energy into electrical energy. So it can be thermal energy that covers coal, oil, and natural gas. So basically these three elements here would be the main source of fuel. Or it can be in terms of potential energy, which can be hydroelectric. Now, it's very important for us to understand this because the nature of the generation sources would determine how we actually manage or how do we actually control which generation to be dispatched. Which one should I run first? Which one should I run later? And which one I should put in on standby. Now, apart from that, there are also other sources. It can be thermal energy, nuclear. In Malaysia, we don't have nuclear energy, but maybe soon one day we will. I'm not too sure whether Indonesia has plans for a nuclear plant. Maybe you probably have one. Then, of course, we have wind energy, solar thermal, and also other sorts of different types of energy sources. Now, these types of energy sources, some can be connected to the grid directly, some may be connected to the distribution grid. So it depends on its function and uses. Okay, so just a quick flow on generation. So the basic building blocks of power plant would be you need to have a prime mover. A prime mover, as you all know, is actually the main thing that actually turns the turbine system. So the turbine system, when it turns, will actually turn the alternator, where you will get your energy source. Now, in order for us to control the generator, this is particularly important because what we are controlling are actually, one of them will be the prime mover. we'll be controlling how much prime mover that we can put in, and we are also controlling how much magnetic field that a prime mover should have as it actually operates. So the main important part here is how do we get the prime mover to turn the turbine. In this particular case, we can have water as the prime mover for hydro plants, and we can have gas for gas plants, or we can have steam for coal-fired power plants. Regardless what it is, the prime mover or the type of prime mover is important because different types of prime mover have different types of response, which means some can be fast, some may take time to actually start, some can be somewhere in between. But regardless, most of the generic generation would have the same concept where you have a turbine system and also an alternator system at the end. And most importantly, for any power system network, we need to control a few elements from a generator. One would be the frequency, second would be the voltage, and third would be the power being generated by the plant itself. Okay, so maybe later I will try to link the three together and see how we can actually understand how things goes. Okay, so just a brief overview on power plants. What you see here will be a coal-fired power plants. And as you can see, the general flow of this power plant would be, I would have my source, in this case, coal. So what do they do is coal has to be crushed and actually being heated up, and that is required to actually heat up water and turn it into steam, and steam goes into the turbine, and turbine turns the generator, and you get power. And the output of the steam goes through a cooling tower and goes back into a condenser system, and water goes back into the boiler, and the whole thing repeats itself over and over again. Now, this is particularly important to understand because in a coal-fired power plant, you cannot get steam immediately. As you all know, for you to get steam, you need to boil water. So if you want to boil water, it takes time for water to boil. And in this case, the steam that you want to get is high pressure steam, or what they call it sometimes superheated steam. So in this particular case, the amount of heat you require takes time. And in most cases for coal-fired power plant, it takes time for it to start up. In particular, some typical coal-fired power plant takes at least between half a day to 1 full day to actually be up and running, because it takes time for the coal to be heated up, and for you to get the right amount of temperature, for you to get the right amount of steam, and so forth. So that's why in most cases for coal-fired power plant, you seldom switch it off. So usually they are being designed to run as base load plant. So where would this base load plant be? I will show it later as we looked at the load curve and see how the hierarchy of what we have. Okay, so we have a coal-fired power plant. Just to show for some who maybe doesn't know, a coal-fired power plant are usually very big capacity. This is one of the biggest in the world right now in China at 6.7 gigawatt. But of course, you have smaller types of power plants, coal-fired power plants. Now, in terms of its emission, the typical standards of coal-fired power plant needs to follow the Department of Environment emission condition, especially in terms of sulfur oxide and nitrogen dioxide emission. So the SOx and NOx has to be within a certain limits, and usually they are being filtered by a series of filters. Some of the filters are electrostatic filters and so forth. Okay, so just to show for some who haven't seen a coal-fired power plant, one of the signature is you should be able to see this ramp here, where this is the ramp where they actually bring in the coal right into the boiler to be fired up and so forth. And usually by the side, they must have a coal mill or a coal storage area. Then later on, after it's being fired up, they will actually collect the fly ash coming out from the smokestack, and they are being stored elsewhere in a sediment pond. And usually the fly ash can actually be used for other products, for example, bricks or other materials as well. Okay, so let's look at another type of power plant. In this case, a hydro type power plant. Now, hydro, as you all know, or what you have learned before, hydro works based on water, where I have water at a particular height. and the water goes down the set of pipes here, which we call the penstock, and goes around the powerhouse, and the water goes out. Now, the interesting thing about hydropower plants is because it uses gravity or potential energy from gravity, and water goes down relatively fast. So basically, it's like you opening up the pipe of your house. The minute you open, water goes out almost immediately. Now, this is very important for you to understand because with this characteristic, we know that hydro plants can be switched on or can be connected faster as compared to coal-fired power plants. So as I mentioned before, coal-fired power plants takes time for it to heat up and be ready to be connected. Hydropower plants can go up even faster. So that's why hydro plants can be used almost immediately. Okay, especially during operation, sometimes what they do is they have a bit of what they call it a spinning reserve spinning, where they allow small amount of water to turn the turbines a bit so that the minute you open the valve, the turbine blades can turn faster almost immediately. So in most cases, hydro plants are usually being used for fast response. Now, however, in places like Malaysia, for example, hydropower is quite limited. We don't have big hydropower plants. So therefore, in most cases, hydropower plants in Malaysia are being used for peaking load, which means to cover the slight increase of load as we go through the load profile for the day. Okay, so this is one example of a very huge hydro plant. This is in Three Gorges Dam in China, which actually taps water from the Yangtze River. And this is basically very big, one of the biggest in the world. It's at 22.5 gigawatt. And it is designed as such that it can run the hydro plant, and at the same time, it doesn't disrupt the natural economy process. As you can see over on this side here, there's a special lane here which they actually designed for ships to go through, because Yangtze River is quite long and they still have economic activities along the river. So they have special water lifts here to lift the boats up so that they can continue their journey upstream. And for the Three Gorges Dam, this is only one of the few dams that they have across the Yangtze River. They have a few set of dams further up. Okay. So this is another type of plant which is called the gas power plant. In particular, it's called combined cycle gas plant. Okay, so why do they call it combined cycle gas plant? Is because, as you can see here, there are two sets of turbines. Okay, one is a gas type of turbine, one is the steam set of turbines. So in this case, combined cycle gas plant must have a continuous source of gas. And the good thing about it, when it's being designed as a combined cycle plant, it is considered to be more efficient because the heat loss that you get, or the heat that you get, is being used for steam to get more energy out of it. In this particular case, gas in its nature is relatively fast, not as fast as hydro. Hydro is like you turn the water, water flows, you get power immediately. Coal, you need to wait half a day to one full day, then only you get enough power. However, gas is somewhere in between because it's not too slow and it's not too fast. So usually gas plants are somewhere in the middle between the load base plant and also the peaking plant. Okay, this is one example. This is one of the currently biggest combined cycle gas turbine plant. Is Jebel Ali at 8.6 gigawatt. Basically, you can see that gas plant can also be as big as you can see there. Now, another one that I would like to add on, which is in particularly quite interesting. It can be quite controversial because of its nature, which is the nuclear power plant. Nuclear power plant, it goes back to the same basic principle that we talked about earlier, where I need to have a prime mover. That prime mover requires it to be in the form of gas or steam. And once I have steam at the right pressure, it will actually turn the turbines. Then from the turbine, you will turn the alternator and you get power. Now, nuclear power plant is actually doing the same thing. As you can see here, you are still heating up water. Water goes to steam. Steam goes into the turbine, and the turbine turns the alternator and you get power. Now, the only difference is how do I actually heat up water? Before this, I use coal fire as my heat source. The other one, I can use gas as my heat source. In this case, I use heat that I get from a nuclear reaction. Now, a nuclear reaction is as such that it consists of nuclear rods in here and also carbon rods to actually control the heat being produced. And if you can recall back, or if you can quickly do a quick Google, the way they generate heat is by the concept of nuclear fission. Nuclear fission means I have an atomic element and I break this into two. And the minute I break this into two, it causes heat. So you imagine I have lots and lots of this happening. And from there, I can get heat. Heat heats up water and turns to steam and turns the turbine and so forth. So the external part of the water goes back into a condenser to change into water again, and the whole process repeats again. Now, as you can see, a lot of nuclear plants have this smoke, has this stack here, tower stack here. Basically, that is to take out the water vapor. It's not smoke, it's just water vapor coming out from the plant. Okay, and of course, a nuclear power plant do require water to actually cool the system down, and usually they have a water source that flows through the nuclear plant itself to cool it down. Okay, so this is one example. Currently, this is one of the biggest plant in Korea, which is the Kori plant at 7.5 gigawatt. And typically, most of this nuclear power plant would actually be situated near a water source because they need water to cool the plant down. If you remember what happened in Japan, the Fukushima incident, where you have a nuclear meltdown in the reactor core. What had happened was because as it was operating, there was a tsunami that actually happened near Fukushima that causes problems in water to go into the reactor to cool the reactor down. So that caused the reactor to have heating problems and they had to be shut down. Okay. Now, the interesting thing about nuclear power plant, you can actually control the amount of heat by controlling the carbon rods that goes into the nuclear reactor. So what about its response? Is it fast or is it slow? Again, because the fact that we are using steam as our main source, steam takes time to actually convert from water to steam. So it's not as fast as gas, not as fast as hydro, but the good thing about nuclear power plant is the size. That means that it has a smaller footprint in order for me to get a bigger amount of power. For example, if you see here, it's relatively small and I have 7.5 gigawatt. If I go back and look at 8.6 gigawatt and you look at the size of the plant here, it's huge. The size of the plant is huge. Okay. And if I look at, say, for example, Three Gorges Dam here, it's even bigger for me to get 22.5 gigawatt. So the advantage of the nuclear power plant is actually the size. The size is smaller and I can get more amount of energy out of it. And the amount of fuel that you use is relatively small. So therefore, most of this nuclear plant doesn't need to be replenished after a number of years. So it can run as normal for maybe 5, 6, or 7 years. Then later only the fuel has to be replenished. However, nuclear plants also has its issues. For example, if I do not manage it properly, I have nuclear meltdown, nuclear radiation, and so forth. I'm sure everybody have heard before on Chernobyl, on 3 Mile Island, and so forth. But if you notice, most of these accidents are actually due to some malfunction of sensors. Maybe they do not actually do the right maintenance and so forth. Statistically, accidents that happen with nuclear power plants are much lower as compared to road accidents or airplane accidents or air crashes. So that means the risk of that happening is actually very, very low. However, due to maybe fear from people, they are worried about nuclear plants, they're worried about radiation and so forth. So they feel that nuclear plants are dangerous. In actual fact, if you talk about nuclear, it's not as dangerous as even using your mobile phone, because the radiation from your mobile phone is also equally dangerous, or you using your microwave at home. So it's all about how do we manage it properly. Okay, so what we have covered just now are the main typical power plants that are connected to the grid. However, there are also other sources here, which is the current trend that is actually happening now. This is one example, which is a grid-connected solar panel. Why do I call it grid-connected solar panel? Because the amount of power that it generates is huge. This is talking about 2.25 gigawatt. This is in India. And grid-connected solar power has its advantage and disadvantages. As you all know, solar power means that you have the rays from the sun hitting the PV panel, the solar PV panel, and that is being converted into energy through your power electronic converters, and you get power going out. Now, the issue about connecting grid-connected solar PV system is just one thing. Well, one of the main thing would be, if I have sun, I have power. If I don't have sun, I don't have power. Now, when do we usually have the sun? During the day. We don't have the sun at night. So that means that at night, this grid-connected solar plant will not work. Or, since we are all in the tropical region, we have monsoon rain, we have very thick clouds. So that means that whenever I have very high cloud coverage, again, my efficiency of my solar panel will drop. Now that causes one of the main concern by utility, because I do not want my grid-connected solar panel to not produce power when I have peaking load. So that means when, let's say during midday, when my load is at the max, I don't want to lose my sun. Well, I cannot control the sun, but I cannot lose power from the solar panel. And this is what they call as the duck curve. Okay, the duck curve, because it looks like a shape of a duck. And due to this, grid-connected solar has to be managed properly by electricity utility. So they need to control, they need to know the weather patterns before they can actually connect grid-connected PV effectively. And they have done lots and lots of research that connecting solar PV is good, but you must have backup systems and contingencies if the solar panel fails to give the required amount of energy. Now, this is another type of solar energy. In this case, it's called solar heating. Solar heating is slightly different. You don't have solar panels here, but you have the sun to actually project the sun rays at the central point here, where usually at the central point you have maybe a container with water that turns it into steam, or oil to heat it up and to transport that heat to a steam generating plant and so forth. So again, because anything that goes with the sun have its issues. If you don't have sun, then it will not work. So again, the characteristic of the solar power plant is also similar to the solar PV plant. So in order for you to connect this together, you need to be careful to ensure that you don't destabilize the network. Okay, apart from the main generation, I also need to deal with what we call distributed generation. In the old days, the distributed generation is very centralized. You don't have distributed generation. I only have power from one power plant that goes to your loads, as shown here on the left. But nowadays, okay, I have the main power plant still here. I still have my loads still here, but connected in the distribution system would be solar panels, would be small wind power plants. I can also have battery storage. I can also have micro turbines, and I also have combined and heat power plant or biomass type of power plant. Now that creates another issue or for you to actually consider, because before this power actually flows from the power plant to the load, only one direction. Okay. Now, it's difficult to predict where power would go, because you can have a big installation of rooftop solar power plants, and that can be injected back into the distribution grid. and as such that it can help to reduce its energy dependent on the transmission grid. However, for you to connect the distributed generation to the distribution grid requires some careful study, because as you all know, since some of you are working in PLN per se, in order for you to protect your transmission grid and your distribution grid, you have protection systems. You have your fuses, you have your relays, and those relays are actually being coordinated. That means that if I have a fault operating here, it will operate here first. If not, it will operate a bit further up, and further up. That's the basic concept of it, so that you can protect the system. But once I have a distributed generation system, as you can see here, power may not be flowing from one direction, but power can flow from maybe from the house to this commercial building, from this factory to the house, depending on where you have the distributed generation being connected. So therefore, when you want to actually connect DG or distributed generation, you must actually consider its impact to the distribution grid. Your transformers may need to be changed. Your transformers may be overloaded when it's being connected. So it's not just about connecting it anywhere. And in most cases, so far, I know so far in Malaysia, we do not have a big distributed generation as such that it will inject back into the transmission grid. Usually that doesn't happen. Or in most cases, our power system watchdog, which is the Energy Commission of Malaysia, has put in rules as such that power cannot be transmitted back into the transmission system, but only circulated in the distribution system. Okay, so therefore, we have to actually consider how it's being connected, and as what you are going to learn today, how it is being controlled. How do you actually coordinate all this to make sure that you still have power supplied to your consumer, your transmission grid are actually working in a safe level, and at the same time, you are not putting risk to your network. Okay, so this is some of example distributed generation. Usually they are very small plants. This is what you call a mini hydro. The characteristic of it is very simple. It's usually located by the side of a river. Then you have the main river flow over here, and they have a side flow over here that goes into a small powerhouse, and that goes into the network. And usually mini hydro operates in small amount of power, but usually has its own problems. Sometimes I have a lot of sediment that goes through the powerhouse, and sometimes I have logs and rubbish that goes into it, so that needs regular maintenance. This is the rooftop solar that we talked about. The rooftop solar can be AC or DC depending on the system that you have. This is quite new. Currently, this is the current trend where we talk about battery energy storage systems. So currently around the world that I know, Australia has a particular market model for this, whereby they have a bank of battery energy storage system where they buy power during off-peak period, which is at night, to charge the battery. Then during the day, they become the generators. They will dispatch power to the network itself. So in this sense, it opens up into a whole lot of different business model. It's no more just big power plants running. It's no more about solar PV and so forth. It's about I charge the battery at a cheaper rate and I sell my power bank at the expensive rate. Okay, so one other thing that I would like to highlight is that battery energy storage system, the business model itself will only work when I have a deregulated system. A deregulated system means that I have multiple power supply, and they will actually sell to the main supplier, which is the grid. So that means that they bid for the price that they sell, and the user can also bid the power that they buy. In Malaysia, we don't have that. In Malaysia, it's very regulated. I have TNB. TNB will produce power, transmit power, and distribute power. I have maybe independent power producers to sell power to TNB, but the amount is small. There's no energy bidding and so forth. I'm not too sure in Indonesia. In Indonesia, it's still it's deregulated or regulated. May I know? Do you know whether it's regulated or currently? I think you only have one, right? PLN is the generation transmission distribution, or
Yes.
you have different companies.
Only one PLN.
Only one
Yes.
PLN. Yes. So it's very regulated. So
Yes.
this type of battery energy storage system may not be suitable. May not be a suitable market for a regulated environment, but it's very suitable when it's in a deregulated environment. Now, regardless the type of energy sources and whatnot, the control of these energy sources is still the same, especially the main generation. Like I mentioned earlier, we need to control the amount of power. We need to also control the amount of magnetic field that it is being managed by the power plant itself. So there's two main elements that you control. The prime mover is controlled by how much prime mover that flows into the turbines. The amount of magnetic field is being controlled by the field current. If you learn electrical machines before this, I'm sure you have learned that before. If I change the field current, I will increase or decrease the magnetic field of my rotors, or my alternator to be exact. So if my magnetic field is higher, so therefore I can get more energy coming out, and lower and so forth. And in actual fact, there is actually a relation between prime mover control and also the magnetic field control, which relates to real power and also reactive power. In most cases, the field windings or the field current will control the Q coming out from the generators. The prime mover controls the amount of P that is being generated by the generator. Now, I did mention the term frequency. Frequency is a little bit tricky to control in a network because it's not being controlled by just one generator. Usually in a big network, we have this assumption or this principle whereby the frequency of the network will determine how fast the generators will turn. So that means that, say, for example, in Malaysia, the frequency is at 50 Hertz. So therefore, all my generators must work to slightly higher than 50 Hertz. I don't work at exactly 50 Hertz, but I work at slightly higher than 50 Hertz so that I can get power transfer from the generator to the network. So that's why monitoring the frequency is very, very important because if the frequency is not stable, then you might actually lose the network. A little bit later, I will talk about the control center or the dispatch center and how it is being monitored. Okay, so transmission, I think you've seen this before. This is just a quick recap where transmission covers from low voltage, medium voltage, and high voltage, and in some countries, extra high voltage. Typically, if you talk about transmission towers, the higher it is, the higher voltage it has. And of course, it has different design. But the principle is still the same. I need to have the right distances between the conductors to ensure that I have sufficient air insulation to avoid arcing. Okay, so this is some of the transmission, a typical transmission tower, whereby usually it has usually two circuits here, one circuit here and one circuit here, and you have the phases here. And of course, I have the shielding wires here and also the neutral over on top. And of course, because it is actually air insulated, that's why it must have specific distances between them. And as you can see, the transmission tower, if you remember, transmission towers are bundled, which means it consists of small conductors here to provide better cooling and also to reduce the weight of the transmission tower transmission line as compared to a bigger cable. Okay, so another type of transmission will be HVDC transmission. In this particular case, HVDC has its certain functions whereby if I have an AC system which has a different frequency, for example, another AC system which is a different frequency. So let's say I have 50 Hertz over here and I have 60 Hertz over here, for example. I cannot just connect the two together using AC because of the two different frequencies. So in order for that to happen, I must have what you call an HVDC transmission line where I convert it into DC, transmit to DC, then convert it back into AC at the right frequency. Now, typically HVDC is very good when I want to protect the network from other network. In Malaysia, we only have HVDC line from Semenanjung, Malaysia to Thailand. But from Semenanjung, Malaysia to Singapore, we have the direct line connection. Now, the reason why we have between Malaysia and Singapore, because we want to actually isolate the Malaysian network with the Thailand network so that any issues in Thailand will not be transferred into in Malaysia. So in the US, for example, they have multiple DC systems to actually protect small parts of their transmission network. In Indonesia, do you have a lot of DC transmission lines, or is just all AC?
Not yet,
Not
Prof.
yet.
Not yet. Okay.
Or in
Only
AC.
AC
Only
transmission.
AC.
Okay. So usually, apart from isolating the network, DC is also good for long distance transmission. The longer you go, if you use DC, the amount of losses will be lesser as compared to AC systems. Okay, so managing this transmission system is also particularly important because you're talking about importing and exporting of power. So that will determine how you design the transmission system and how do you actually manage the import and export of power. So this is just an example of the HVDC converter. Usually now they have multiple banks of IGBTs. So in here you have banks of IGBTs to actually do the converter, because it's high voltage and high power. I cannot just use one IGBT. So they have a series of IGBT banks to actually distribute the power that can be handled by those IGBTs. And in fact, the transformer that they use are also special types of transformers, something like a 3-phase to 6-phase type of transformers to manage this converter station as well. Okay, so based upon what we have covered on generation and transmission, there's this element which is also important when we manage dispatch, would be the generation mix. Now, what I've shown here in Malaysia, we have a typical generation mix where the biggest generation sources would be coal, gas. Second would be, the third one would be hydro, and the rest are usually small ones, okay? Oil and diesel we still have, but it's very small. But the three main elements will be coal, gas, and hydro. Now, this relates back to what we covered just now, whereby coal, as I mentioned, in Malaysia, we use it as a base plant because it takes time to switch on. So therefore, it turns on all the time, 24/7. Then on top of that, I will have gas. That's why you see gas here is the second largest, or the largest as well. That goes above the base load. And then the hydro will function as the peaking load. It will cover all small increases or decreases of energy demand in the load profile. Why we use hydro to do that? Because of the response is very fast, and that's particularly important. Okay, so over what you see here is a general transmission network for the peninsula of Malaysia, Semenanjung Malaysia. And as you can see here, here's the DC link that connects from Gurun to Thailand. Gurun is in Semenanjung, and here, this point here is called Klonge in Thailand. And over in Singapore, there's the connection point here, which is in Johor Bahru. Now, as you can see here, I think it's the same for even Indonesia. You notice that the transmission lines are actually not everywhere. It is actually at main load points. If you can see here, there's a big one here in Pulau Pinang. There's one here in Kuala Lumpur, in Selangor, here. You have some here, and also the next big one here in Johor. So because of that, these three main points are what we call the main load centers that has to be taken care of. However, my plants are not located at this point exactly. Some of them are actually located here in Kelantan and in Terengganu. Some are also located at different regions of the country. So therefore, how we actually control which generator to run first, run second, run third, and run fourth will depend on its location, its capacity, and also how fast it can actually respond. So usually every day, the dispatch schedule will be different based upon agreement between TNB and the power plant, and depending on which one that they actually want to run first. Because regardless what in dispatch, most importantly, frequency must be maintained, voltage must be stable, and also there shouldn't be any thermal overloads. You can take care of all this, then basically your system is actually stable. And you must have sufficient reserve to ensure that any sudden increase, the system can manage immediately. Okay. All right. So moving on. So just a bit on the distribution system. So I think you've seen this before. Just a recap. There we have the distribution system connected directly from the grid. In some places, I have an MV system, then an LV system, depending on what you have. Regardless, this whole system here, or basically the transmission here, is governed by what you call a grid code. In Malaysia, we have a grid code that governs the standards related to transmission system. And we also have a distribution code here that covers the distribution requirement or distribution standards that is required for the distribution system. And I believe in PLN, they should also have a grid code or grid standards and also distribution standards. And usually these grid standards are not exactly the same as other countries, because your system that you have will be suited to what is suitable for you, because maybe your percentage of deviation required can be maybe 10% or 15% or plus minus +5 or -10% deviation, depending on the capability of the network. For Malaysia, is typical, is about +5 and -5. Okay. So going back to the third element, which is also important when we talk about dispatch, would be understanding load. Now, the type of load that you have, we usually have three types, main component: resistive load, inductive load, and capacitive load. So each of these three different loads will have its own different characteristic. Resistive load is usually very linear. Inductive and capacitive are non-linear. Now, based upon these three basic loads, it will actually be used to understand the different types of power systems load. Typically, you should have a domestic load. In this case, domestic load relates to residential. You should have also commercial load, which relates to maybe medium industries. Or you can have industrial loads, which also relate to big factories. You may also have agriculture load, depending on countries. So it depends on different design or different practice of each country. Some country may also have another load. They can call it traction load for electric trains and so forth. So understanding the type of load is important for you to actually be able to understand how it behaves. And once you know how it behaves, then you can effectively manage this load. Okay. So this is an example of load composition. Okay. This one here is this one. The top one here is from TNB. This is an old data that I got, which is from year 2004 to 2007. And as you can see here, for Malaysia, the load composition that you have, based on the three, which is commercial and domestic, takes up about half, and the other half comes on or relates to industrial. So in terms of amount of power, you can see that the industrial takes about 47%, commercial 18%, and domestic around 18.96%. Okay. Now, however, the amount of customers, the biggest would always be domestic. Even though the power is not as large, the biggest number of customers will be domestic. Now, why this is important? You need to actually understand that each place in your, or each place or each city will have different load composition. Some city will have high domestic, lesser industrial. Some will have more industrial, lesser domestic and commercial. Now, this is particularly important because the type of load that it projects will be different. For example, when we talk about domestic load, you're talking about more resistive and inductive load. And the inductive load will not be as huge, purely resistive, and you wouldn't have a lot of power factor problems because typically any domestic house, you only have small pumps, just maybe for your air condition, for your water pump, and so forth. Most of them will probably be heating load or lighting load and so forth. When you talk about commercial, maybe you have some slight variation, maybe more pumps, slightly bigger pumps. But when you go to industrial, this is where you have power factor issues, where you need to have capacitor banks, you check for power factor. And I'm sure for industrial, let's say for in Malaysia, we have a special meter for industries where we measure the power factor for the industry and they have to control the power factor at a certain point. If they go beyond this power factor point, they can be penalized by TNB because they'll be taking extra reactive power from the grid, which if we go back earlier when we talk about generators just now, it relates back to the field current being generated by the generators. And if it takes too much, my field current is overloaded, damage to the generator is more expensive than putting in a capacitor bank. Okay, so another example here, this is from Sabah, which is SESB. So in Sabah, you can see the breakdown is a bit different. I have more commercial, more domestic, and smaller industry. So that depends on what you have in the particular area. So I guess in Indonesia, you probably have a different load composition for the Jawa Island, maybe a different load composition for northern of Sumatra or southern of Sumatra, or Kalimantan will have different and certain parts and so forth. So therefore, that will tell you on how should I manage this power demand and also Q demand from the network. And Q is particularly important to manage because if you don't manage Q properly, then you will have voltage problems as you run the network. Okay, right. So combining the loads that you have learned and that I have covered just now, then it relates back to what you call the I will call this the load profile. Okay, so this is a typical of the grid load profile for the national grid in Malaysia. This was taken from the annual report that they published in 2005. It doesn't matter, 2005, 2023, 2022, the general shape would still be the same. Maybe the magnitude and the detailed flow or the shape would be slightly different, but the overall shape would still be the same. And I would say majority of the countries would have similar load profile for the grid because it has the same set of interaction, which starts typically around 8 o'clock here, okay, where it's the load will usually start to pick up. This is when people starting to go to work and factories starts to start their engines and their motors and pumps. Then later until it reaches its maximum demand somewhere here, then usually you can have a dip. This is when factories shut down for a while for lunch. Then later it winded down in the afternoon and goes into the evening. So this is in particular quite good to understand because this is where we want to do the dispatch. Okay, let me change this using, let me try and get a pen. Remember that I talked about the base load plant, which is the coal-fired power plant. So that is usually being used somewhere here. Let me mark somewhere here. Because for coal-fired power plant, it is always constant. So therefore, coal-fired power plant becomes the base load plant. So it always runs all the time. I do not need to control it too much, but I do have some control a bit, but usually it's constant. Then after that, I have what you call the gas plant, which is somewhere in between, remember? So let me get another pen color, just a minute. Let's say blue, okay. So base, the second level, which is your gas plant, are usually, oops, sorry. Where is my cursor? Oh, here it is. Usually it's here, somewhere here. Sorry, my scribble with the mouse may not be nice, but shows the idea. So usually this blue area will show where I will operate my, probably not quite accurate. Let me Let me add a bit. Just a minute, it goes up here. It usually follows the load profile. Usually it goes up. Sorry, it goes up, and it tries to follow as close as possible. Okay, so this is where the gas plant will actually work. Then the balance is the area here. Just a minute. Let me get a different color pen. Green. So the area here, and here, and here. Okay. These are usually being managed by the hydro plants, which they call it, or we call it as peaking plants. So the hierarchy at which generator runs first, second, and third is important, which goes back to the concept of dispatch. Since you are also looking at the concept of power dispatch, each of these plant has its own costs. Some of it is cheap, some of it are actually expensive. So usually as a utility, you want to make the most profit, you always use your cheapest plants first. Then you use the expensive plants a little bit later. So that's how you actually arrange your generator ranks as you operate over the day. Okay. So in order for you to determine the generator ranks, you need to know the cost of each plant. And from the cost of each plant, then you need to also consider contract between the plant and the utility. And then from there, you set your hierarchy or rank. And usually the price that the plant sells back to the utility is confidential. It's in the contract. You don't tell people. Only TNB or only the utility and the generators would know. Okay. Now, apart from cost, they have to also make sure stability is maintained. They have to make sure that the network is not congested, the network is not overloaded, and so forth. Okay. Right. Let me move forward. Okay. So based upon that, we talk about different loads. So here we talk about some basic elements of load modeling. So in load modeling, there are a few elements that you need to take into account. Just a minute, I need to check so that how many minutes more do I have? Can I check how many minutes more do I have so that I don't overshoot?
Until 9 p.m. Prof.
Until 9 p.m.
Include the Q&A session.
Okay, all right. Because sometimes I can talk too long. Okay. So in the load curve, as what you can see here, this is what you call, let me get my pointer again. So this is what you have, what you call a demand curve. A demand curve basically represents the demand of the load that the generator must meet. So that means when the power demand goes up, the generator must give that power. Now, what will happen if the generator cannot give that power? If you remember the concept of electrical machines, when the amount of load goes up and the amount of power given to the generator is maintained the same, what will happen is the generator will slow down. Okay. A simple analogy, if you can't remember, a simple analogy that I use is that if you are actually cycling, okay, you are on your bicycle, you cycle at say a constant speed, same speed, okay, no change. Then suddenly something appears on your bicycle and makes it heavy. If you don't change your energy to change your cycling power, your bicycle will slowly slow down. Okay, so that means you don't change anything, your bicycle will slow down. So the same thing goes to here. If the load suddenly requires more power and I don't give anything to my generator to give that extra power, the rotor will start to slow down. So therefore, the frequency of the network will start to drop. So in order for that, I need to increase my prime mover to come in so that my rotor will turn faster and my frequency will go up again. So that's why in the power system network, you always monitor frequency as one of the elements, because I cannot make my frequency to go too low and my frequency cannot be too high. If I have too much generation power, not enough load, frequency will go up. If I have more load, but not enough power, my frequency will go down. So that's why having this load, having this demand curve is very important, because I need to tell the generators when to switch on, when to actually switch off, when to increase power, and when to reduce power, so that I can always continue to meet the demand here, and at the same time, I can still maintain the right frequency. Okay, so we need to have the demand curve, and all the demand curve must have what you call the maximum demand. That means the maximum power that the load requires for a particular time. Okay, so based upon that, there are certain factors that you can actually derive from there. This one here is called the demand factor. So the demand factor is actually the maximum demand, which is the peak demand that you get for the day, divided by the total connected demand. So that means that maybe the maximum demand for the day is 50 megawatt, but then my total connected load is actually 100 megawatt. So therefore, the demand factor will be at 50%. Okay, so this is the demand factor. You also have what you call the utilization factor. So that means that it's a ratio between the maximum demand divided by the rated system capacity, which means what the system can actually handle. Okay, so that covers on how many percent it is actually using in terms of resources. You also have this term called the load factor. So load factor is usually over a specific time, and that covers the average load divided by the peak load. You also have the diversity factor. So this one covers individual maximum load. So let's say I have 10 different types of load connected. Each of it has its own maximum demand. I combine those maximum demand and I divide it by the maximum system demand for the system itself. Then, of course, I also have the loss factor that covers the average power loss and power loss at the peak load. So all these elements needs to be taken into account when you actually try to model the load itself and understanding the load. Okay, so this is some example what we cover in terms of load diversity. This is just based upon this example here. Let's say I have a network, distribution network, and I have customers here, and each customer have its own load profile. Okay, this is customer 1, customer 2, customer 3, and customer 4. So this would be the combination of all the customer load. So this is total of 1 plus 2 plus 3 plus 4. That gives you the total. So diversity here covers the total connected. Okay, if you look back at the formula here, diversity factor is the sum of individual maximum demand over maximum system demand. So that means each of these has its own maximum demand here, 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 and here. You add all those maximum demand, divide by the total system maximum demand. So in this case, diversity factor is at 1.56. Okay, so these are some examples just to understand load diversity. So what I'm trying to tell you is that in order for you to effectively dispatch power, we need to understand load and load behavior. We need to understand the generator and the generation behavior. But of course, if you learn power system studies in any of the power system textbook, you will actually learn this chapter called power system dispatch. It depends on what textbook you use. That depends on different chapter. Over here in Unit 10, we use the Hadi Sadat textbook. So usually in this power system dispatch, they only look at the economic model, because that economic model just look at cost. That means that I have a demand, I have my generation, so I must dispatch my generation to meet the demand, but at a function where I can have cost reduced so that I can get the maximum profit from it. So that is the basic concept of power system economic dispatch. However, once you have that dispatch schedule, you need to run through the network and check for its stability. Typically, when you run the network, you need to check for frequency, you need to check for voltage, and you need to check for thermal overload. Okay, so frequency, let's say I take example for Malaysia. For frequency, I must make sure that it is at 50 hertz. It must not vary too much. Must not vary too low. And then voltage is particularly important. I must make sure that the voltage value is at 1 per unit. At most, maybe it can go up to 1.05 or maybe at zero or as low as 0.95 per unit. But again, that range will depend on the network. Excuse me. So I know that certain countries, maybe they can go as high as 1.1 per unit. It can also go as low as even 0.7 per unit, depending on the unit capabilities. So therefore, understanding the load and generation and the economics of it is important. The next part is once you have the dispatch model, you need to run through the power system simulation to make sure that it works. Okay. Now, talking about power system simulation, it covers, as you all know, you've done power system load flow before. Load flow, as it is, covers static. Let me check again. You all have done load flow already, or you haven't done load flow? I check with the lecturer.
Load flow is done in the section before, Prof.
Oh, you have done load flow before, yeah? Okay. So since you have already done load flow, and if you remember, load flow are actually what I call it as static load flow. That means that you model, sorry, all models that you have is actually not time-based. Means that you have generated this much, you have load this much, and you have your losses this much, and that is the same over time. So that is static load flow. It's very good and very fast for you to do the analysis. However, there are situations where you need to upgrade that static load flow to go into dynamic simulation. So dynamic simulation where your models are actually based on time, and you want to see how the generator behaves. You want to see how the rotor speed goes up and down as you have changes in the load. So that should also be done, and that's usually done by the utility to make sure that the system is stable. Just doing static load flow is not enough. Usually you need to do more by doing dynamic simulation as well. Another point that I wanted to mention is that once you have the generation dispatch and the load model, the other part that you need to actually consider would be the contingency analysis. Now, contingency, have you done contingency analysis before or haven't?
Maybe
Have
in
you
the implementation in the work.
Okay, all right. So, for those who don't know, contingency analysis is actually, I have a network, and let's say I take one element out from the network and I test. Will the network be stable or not stable? So that is what you call N-1 contingency. I can also have what you call the N-2 contingency, where I take two elements out, then I test whether the system will be stable or not. So usually or every day, the system operators or the network planners will always do this test because they have to make sure the system is always stable all the time. But of course, you have computer softwares to do it for you, and they can actually do quick contingency analysis for the system, and they will tell you whether your dispatch plan is safe or not safe. Okay, so focusing back into load models, when you talk about static load flow, the model is very simple. In static load flow, your model is just P load and Q load. That's it. Okay. However, when you go deeper into load profile and load models, there are actually different ways to model the load. Because when you go into dynamic, the type of how you model that load will be important to represent that load itself. Okay. So in this case, we have different types of classification of loads. It can be static load models, means the load model that is not dependent on time, which is your P load and Q load. So in this case, they have different ways to actually do that. This is called the zip model, exponential model, frequency dependent model, and EPRI model. You also have the one that depends on time, which is induction motor, load recovery, composite load model, and so forth. And nowadays, sometimes they also look at AI-based models because they cannot actually accurately model it based on the R, C, and L. Usually they use AI to do a combination of it so that they can model it as accurately as possible. So this is just to show you what are the components of the zip model, exponential model, frequency dependent model, and also EPRI model. So EPRI actually comes from a research institute in the US. It's called the Energy Power Research Institute. It's one of the well-known power institute in the US. And also some of the models that they use are also being used by other countries all around the world. So they looked into different load models and try it out to see how best it fits into the network or how best it represents. And this is very important because the more accurate your model is, the more you can manage your power dispatch better. So therefore, you have lesser waste of energy. Okay. Okay, so this is some example of a dynamic based model. This is a simple model by an induction motor. It's actually not too complicated if you remember the induction motor characteristic that we learned in electrical machines before. It covers how the power is increased and what happens as the motor reaches maximum torque and as it goes further up. Okay, so in this case, it has its own power profile, voltage profile, and also its Q characteristic. Now, induction motor is important for you to understand how it links up to the load model because in the network, we have a lot of induction motors. If you use electric trains, they are one source of induction motor sources. If you use water pumps and so forth, there's also another source of induction motors. So when we talk about industry, having this induction motor model is very important so that you can estimate the Q demand for the particular industry and you can manage the network design to meet the requirement. Okay. So this is one example of a load model, of a component behavior. In this particular case, it relates to a tap changing transformer. The dotted line here covers the different tap settings that I have for a transformer. Then as I change my tap setting, my load power will start to shift according to the profile that I have. So it has a particular shape as I increase my tap changer. Okay, so that characteristic is also important when you want to go into more detail in terms of dynamic analysis and so forth. Okay, and nowadays when I have a lot of PV and more distributed generation, a lot of tap changing concepts are being applied back to the distribution network to control voltage and ensure that you have stability in your distribution system. Okay, so knowing all that it goes back to system operations and planning. So in Malaysia, we have two departments, which is system operation and system planning. So what do they do? Both of them focus on the same thing. They want to make sure that my power system network is reliable. This is the keyword. It has to be reliable. When it is reliable, it is able to deliver power from the generator to the consumer at the required standard and quality. Now, how do we know what would be the required standard and quality? Again, it refers back to the grid code or standards in your country. For example, in Malaysia, the standard frequency must be 50 Hertz plus minus 5% or 10%. It has to be at a certain voltage level. Let's say if it's 1 per unit, it can go as high as 1.05 or as low as 0.95. So that is voltage and that is frequency. And of course, quality, maybe there is a specific harmonic content that cannot be there. This is particularly important for distribution system because harmonic comes from motors and machines. So therefore, if you don't control harmonic in your power supply to the distribution system, so therefore your supply is not of good quality. When it is not of good quality means that if you have sensitive equipment, it may not function properly and it can also damage the equipment. So that's why you cannot put industries which uses sensitive equipment, say for example, semiconductor companies or industries beside a metal smelting plant. You cannot do that because metal smelting plant will create a lot of harmonics to the distribution network and will cause problems to the semiconductor plant. So that's why you notice in the place where I have semiconductor plants is all the same type of plants all nearby. Big industries is all big industries nearby, so that I can control the harmonic flow in the distribution network. Regardless, everything is to ensure that it must be uninterrupted and it must be reliable. Okay. So let's say, for example, you take 99.9% reliability. If we look at the formula, it translates to 9 hours of supply interruption per year. So if in a year, we have outage of 9 hours, so therefore our reliability is at 99.9%. And for some countries, that is not good enough. It has to be 99.9999% because you want lesser interruption. Okay. So that's in terms of the operation of it. Then it goes back we also relate back to system planning. So system planning does not look at the day-to-day operation. It plans for short term, medium term, and long term. Okay. So it covers maybe what do I need to add to the system? What else should I put to actually strengthen the system and so forth? And whatever it is, I must reduce my costs. Because if it costs too much and I can only sell that much electricity, then I will not be making enough money. Okay. So what we have here, usually in any network, we have what you call short-term, medium-term, or short-term and long-term planning. So short-term planning are usually short duration within a year or two, whereby they look at what slight improvements that I can do to the network so that I can meet the requirement. It also have the element here which is called load forecasting. I will show you a bit later on load forecasting and how it also relates on short-term planning. So this is one example of a load profile for Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, and Sunday. And as you can see here, these are all at different times of the year. So notice that the shape for Monday is different for different times of the year. Some are higher, some are lower. Same goes for Tuesday, Wednesday, Thursday, Friday, Saturday, and Sunday. Now, for certain countries, this is sufficient enough, but for certain countries, you have extra complexity. For example, in Malaysia, for example, I know for Malaysia is a problem, is we have the usual load curve on different days. So we only have 2 seasons, rain and no rain, right? I think the same for Indonesia. Hot or not hot. So that creates one change in the load profile. Secondly is your festive season. Your Hari Raya Aidilfitri, your Hari Raya Haji or Aidil Adha, your Christmas holiday, school holiday. I don't know what else holidays that you might have. Now, some of these holidays are fixed. For example, Christmas. Christmas is fixed. You know Christmas on 25th December, fine. But when you talk about Chinese New Year, Hari Raya Aidilfitri, and for the Indians, we call it Deepavali. Okay, those festive season, they move with the calendar. So sometimes you have Hari Raya and Chinese New Year together, very close. Sometimes you have Hari Raya and the school holidays very close together. So because of that, it creates different variations of the load profile. Because during holiday, I think the same anywhere around the world, factories will shut down, people will not go to work, and people will go back and balik kampung, go back to your kampung, balik ke desa, and then from there, you can see a shift of load from the city center to the urban, to the suburb or to the village area. So network operators must actually take care of that. So that's why we have this term called load forecasting. So load forecasting is another element whereby they try to predict what will be my load in the next 30 minutes, what will be my load tomorrow, what will be my load next week. Why? Because once I can forecast what my load is, then I can plan. Do I have enough generation or not? Do I need to add a bit more? And so forth. So in any utility, they have a special unit that looks into load forecasting. Can be short term, every 30 minutes forecasting, or it can be every hour forecasting, or it can be daily forecasting, weekly forecasting, and so forth. Okay, and it's very important because it will ensure that the utility is always ready. Okay. We also have what we call long-term planning. This is further maybe 10 years, 15 years, or 20 years ahead, because it takes time for you to build power plant. You cannot just go and buy a power plant and install tomorrow. It takes a few years to build a power plant. It takes a few years to build transmission lines. So that requires long-term planning. Okay. With all that, in terms of operation, we need to have system operation and monitoring and control. So typical any utility will have a control center. In this case, it uses SCADA, which is it means supervisory control and data acquisition. For Malaysia, we have transmission control center. We only have one, which we call it National Load Dispatch Center. But we also have regional control centers that controls different regions. And this regional control center have even more control on the load. You can do remote switching and so forth. The National Load Dispatch Center usually controls the main big generators and coordinate the generators. This is an example. This is for the National Grid UK, example of their National Load Dispatch Center. Usually it's a very serious environment. They have to focus all the time. You never get holidays. They work 24/7. Hari Raya or whatever, there's still somebody there to work. And they monitor everything from the news to the weather to even football. Because I can tell you it has happened in the UK. You know, the British, they like to watch football so much, right? So during halftime in one of the match, they noticed there was a slight drop, a slight increase of load demand in the UK National Grid, simply because everybody during halftime will go to the kitchen, switch on their kettle and make water, make tea. So even those small behaviors can also create problems to the network in a big way, if it's a lot of it lah. So that's why knowing the load forecast and the load profile is very, very important, because these people working here must know which generator that they have to dispatch, which one they have to increase, which one they have to reduce. And all in all, they have to make sure that frequency is maintained, voltage is also maintained, and there should not be any overloads in the network. Okay. So let me look at the time. I think this one here, I'll just skip through. This is just how do you actually monitor performance in the network. There are several methods of measuring. You have SAIDI, SAIFI, and KAIDI. I take an example of SAIDI here. SAIDI is the number of customer interruption and the duration total divided by the total of number of customers served. SAIDI is the usual index that is being used by a lot of utility around the world. So I give you one example here. This is a SAIDI calculation for different types of utility. The smaller the number, the better the SAIDI value. So that's why you see here, Singapore in 2008 has a SAIDI score of 1.14 minutes, which means 1.14 minutes of outage loss per customer per year. So that's how good you can actually go. Okay, Korea here is 2.2, and if you go down the line, this is Sabah in 2008 last time. They are at 1,078 minutes per customer per year. So that means that literally they have outage every day. Maybe at different parts of Sabah. But now they have reduced it a lot. I think to maybe 10 or maybe less than that. 10 minutes or something less than that. So for utilities, having this ID is important for you to see your performance. And if you can control your network properly, you can actually control this. If your network is efficient, you can control this to be smaller. That is an indicator that your network is good. Okay. So this one here are just future trends. Remember just now we talked about distributed generators. So now it's getting more and more complex. So that's why now we have the concept of smart grid now being coined all over the world. Smart grid helps a utility to manage different distributed generation sources with the same target, which means power must be stable and reliable. Same concept, but it's just they reduce it into a smaller package. Now, as it gets to be more complex, you need to manage better information. Now we have digitalization, so therefore cybersecurity now is an issue. There has been incidences, utility being hacked, and that causes major blackouts in the country. This is also another concept. Can we self-heal a system? And now here talks about different technology, and I'm sure the same thing is currently being considered in PLN as well. Okay, so current trend, this is related to Malaysia, so maybe in Indonesia will be similar perhaps. We are talking about more green, more renewable energy. We are thinking whether should nuclear be there. And the most important thing, we want energy efficiency so that you optimize the energy that you have. All this has its pros and cons, but the most important thing, it has to be managed properly. Okay, so these are the new types of energy, new types of tariff methods, and different types of power system models, whether it's regulated or deregulated. Okay, so I think that's all from me. I think we have about what, half an hour of Q&A.
Okay.
So maybe if anybody wants to ask questions, you can.
Okay, thank you, Prof. Izam, for the outstanding presentation. So our insight has increased about how to setting the operation between load and power plant for every types of power plant required. So we will continue to the Q&A session. Is there any question? Mr. Sutrisna Dwi Putra.
Okay, thank you, Miss Ginas. Good evening, Professor. Thank you very much for your presentation tonight. First of all, I want to introduce myself. My name is Igusti Ngurah Agung Sutrisna Dwi Putra. I work in PLN, especially in transmission division. I stay in Bali. I very interesting to learn, especially in transmission. In Indonesian, use AC transmission, but in your presentation, explain about DC transmission. I want to know more benefit if in PLN use DC transmission. For nose in Bali, people like playing kite. Kite maybe disturb distribution because make short circuit in cable in transmission. So we have KPI to reduce SAIDI or SAIFI. Maybe Professor can explain me more benefit if we use DC in transmission especially. Thank you very much for time. Thank you, Miss.
Okay, thank you. Okay, so DC, as I mentioned before, is very useful when I have two different systems that I want to isolate. Because let's say if I have a big network, let me go back to my, let me try to show the Malaysian network. Yeah, just a minute. Yeah. Share. Yeah. Okay. So let's say, for example, here, right, for the Malaysian network, for Malaysian network, if I want to use DC, is usually to protect between two major subsystems. For example, Thailand. Okay, Thailand will have its own network, so therefore it has its own issues. For example, it may have different harmonic issues or different frequency or different standards or quality of supply in Thailand. So if I want to isolate that issue with Malaysia, I can use that by using a DC link here, so that I can actually block queue and frequency problems that is happening over in Thailand, and I can isolate the system I have in Malaysia. Why? Because as you know, an AC system has frequency, right? Has frequency and have P and Q flow that follows through as it is. When we talk about DC, DC has no frequency. And whatever that you have, I have filters that covers before and after, and I have the converters that actually do the conversion and so forth. So literally any harmonics that comes in will be filtered off, and you can actually isolate the system properly. Now, back to the issue, if I want to have, let's say for Malaysia, oh sorry, tergerak pula. Mana tadi? Sekejap ya, mana? Sini. Okay, so if I want to, if my system is small, for example, Malaysia, Malaysia, the system is very, very small. So therefore, my loads that I have to consider here are not very critical enough for me to utilize HVDC, and doesn't go long distance. Okay, maybe at most it goes 100 kilometers or 200 kilometers before I reach to another substation. So therefore, it doesn't maybe be an advantage to have an HVDC system in the Malaysian network. However, we use HVDC just to isolate the system from different parts of other countries' network. But you must be wondering why in Thailand I have one HVDC connection, but in Singapore I don't have any HVDC connection. It is because in Singapore the power supply quality is good. Then when I interconnect, I don't have issues to my system. So therefore, I do not require an HVDC connection. But in Thailand at that time, TNB was worried about power quality issues coming from Thailand side. So therefore, they installed HVDC. So back to Indonesia. Now, in Indonesia, it would depend on where or how your network is being connected. Let me try to understand your issue. Yeah. So let's say, let me get a map of Indonesia. Just a minute. Let me do a quick Google. Map of Indonesia. Okay, let me share this. Okay, so let's say I choose one map of Indonesia, for example, let's say here. Okay. It's not very clear, but as you can see here, right? I have Thailand, I have Malaysia, I have Indonesia over here. So let's say I want to connect Indonesia, Malaysia, Thailand. Okay. Or probably you want to connect Thailand and Indonesia. So you know that maybe Indonesia has some issues on its power, but then you want to have that interconnection so that you can actually leverage on what Thailand has for the Indonesian network. So therefore, I can also consider having an HVDC link connection here as well, so that I don't have to worry about frequency fluctuations and standards and quality of the network. In Indonesia, everything is running at 50 hertz, correct?
60
Yes,
frequency.
It's running at
50
60.
hertz.
60, yes, 60
60
frequency.
everywhere or only at certain parts of Indonesia?
Everywhere in Indonesian frequency 60.
60, 60.
50,
Yes.
60 ke 50?
It's 50.
50 hertz.
50 hertz for the whole of
50.
Indonesia.
50 hertz.
50. Okay. So kalau semua frequency is at 50 hertz, then you may need not to consider HVDC because of frequency changes. No need to worry about that.
Yeah.
But however, if you want to protect the network, say for example, I want to protect Sumatra and Java, as such that I don't want, let's say Java has a bad network whereby power quality issues are bad over here, and I want to make sure it doesn't go to Sumatra. So therefore, I can also consider having HVDC link over here. Or if I want to export power over long distances, let's say from Kalimantan to Sumatra or Kalimantan to Java. So therefore, the distance is very long. Having an AC line may not be feasible because of the losses that you might have. Therefore, you can look at HVDC links as well. Okay, so that is generally how you need to decide. But of course, HVDC link has its problem. Dia mahal. It is expensive.
Yeah.
Because you ada converter. Converter dia tak murah. Converternya mahal. Dan protection system dia pun complicated. So, dia kena balance lah. Cost untuk buat dengan apa yang you nak achieve. So, itu goes to the economic of it balik lah. Okay. So, I hope that
Okay, thank you.
can explain to you on that HVDC.
Okay, Prof. Maybe I have a question. I'm curious
Okay.
about the transfer of electrical energy from Malaysia to or from Thailand you just mentioned.
Okay.
Is it one direction or not? And how about the sell and buy regulation?
Okay. So, because you notice, Peninsular Malaysia has connection to Thailand and also has connection to Singapore. So that means there is an exchange of power between Thailand, Malaysia, Malaysia, Singapore. So your question is it one direction or two direction? The answer is two direction. So what they do is they will monitor the power flow at those border, whether it goes in or out of Thailand or in and out of Singapore. Then they have a specific agreement between the countries to say that if the change is only this much, I will not charge the country. If the change goes beyond, then the country can charge that extra power that you have. So the advantage of this is that if you have contingency, when you are interconnected to another country, you can actually buy power from that country because buying power can be faster than dispatching a generator to run. So that's why I believe, I think last time in the ASEAN, they were talking about the ASEAN grid to connect Thailand, Malaysia, Singapore, Indonesia, Kalimantan, right up to Vietnam and so forth. Because they want to take advantage of the interconnection. I think the same goes in the Europe. They have done that, the European grid, so they can buy and sell electricity. So that means that you don't need to build too many power plant. You can just buy from your neighbor. That is cheaper and easier in the short run. Okay. Oh yeah, one more thing. You also buy P. You can also buy Q because Q is also required to manage stability. P is what runs the equipment, but Q is required for stability. Okay.
Is there any question from the audience? Boleh bertanya menggunakan bahasa Indonesia ya? Mungkin Pak Rangga Prasetya, raise hand.
Okay, thank you for the opportunity. Am my voice is clear?
Yes, okay, I can hear you.
Yeah.
Okay, thank you. Before that, I apologize if there was my wrong understanding in capturing the learning that you convey, Professor, because I have a bad signal problem while the meeting is running. Poor network quality always pop up in my screen. So earlier, you mentioned about the power system reliability, and I'm quite interested in the nuclear power plant. So in the context of load shading and demand response strategies, what are the key difference in managing primary and secondary loads in the nuclear power plant compared to the other conventional power plants? And how do the difference affect the overall system performance and reliability? Thank you.
Okay, thank you for your question. Now, you talk about managing loads and load shedding and whatnot. So that is one element. The other one is managing the generator. So that relates to generator dispatch. So if you go first on the load shedding or management of the demand, that depends on the decision to actually do the shedding would depend on the network constraints that you have. So that means that if I want to make sure that my network is stable and has a reserve capacity, then I may want to shift my load to other places. Say for example, yeah. Let me open up my slide on the load profile. Just a minute. Okay. Let me share that. Slideshow. Okay. So if you remember, this is the load profile. So let's assume that this is some load profile of a particular area. Okay. So as you can see, I have a low load area, low load condition, low load period here, higher load period here, and low load period here. So there is one element, what they call it, demand side management, where I want to shift my peak to this side here. So that means we talk about load shifting or peak load shifting. Now that is usually done to make sure that my overall load is as flat where possible, because when the load is flat, I can manage my dispatch easier. I don't need to have very complex control and so forth, because the lesser I do changes, the much easier for me to manage. And at the same time, if I will be able to shift this to over here, I have more reserve that I can play with, because reserve is also important to make sure that I have sufficient extra supply if suddenly there is a require for more power. So typical, you don't operate your power system network at maximum. Let's say I have 20 megawatt, my load is at 20 megawatt. You cannot do that. You must have a reserve, and this reserve is what you call spinning reserve or capacity reserve, depending on the definition that you use. Now, going back to nuclear power plant. Now, as I mentioned before, if you look, if I go back at the picture here of this nuclear power plant, okay, you see that the nuclear power plant operates very similar to a steam power plant, whereby I need to heat water, water turns to steam, and it turns the turbine and the alternator. So that means that gives you one indicator. It takes time for you to heat water, regardless whether it's nuclear or coal-fired power plant. Maybe nuclear is slightly faster because the energy you get is maybe bigger, but you still need time for water to turn to steam, and steam turns the turbine. So that's why in other countries who has nuclear plant, they run it as base generators, okay? Because I don't want to touch this. I just want it to run, and that's it. I probably need to control a bit on the amount of heat that I get by playing around with the control rods to make sure that I control the nuclear fission. So therefore, in terms of managing the load, usually if I go back to the load profile that I have, where is it? Oh, sorry, here. Okay, that's what I showed just now. I have the base load at the bottom, then intermediate that follow the curve, then the peaking generators that follows the different small changes here. So if I am an operator, I will put nuclear down here as the base load so that I don't have to change anything. So referring back to nuclear power plant that you asked just now, usually we don't control as much because their behavior is similar to a coal-fired power plant. Okay, so usually demand side management will affect the medium or the peaking generators because you probably use less of that. But the better you manage your load, you may not be able, you may actually be able to use lesser of gas plants and so forth. But usually base load, you always run as high as you can. Okay, so I hope that explains.
Okay. Thank you, Professor. That's really
Okay.
answered.
All right.
Okay, maybe one more question from Miss Pravita Ramadhaniar, please.
Yes, here I am. Okay. Well, good evening, sir. My name is Pravita Ramadhaniar, and I'm currently work at PT PLN Persero. And I'm very interested about the discussions that held here. So if we talk about distributed generations. And we know that centralized utility of today is start from central power station, and then it goes through distribution to house, factory, and commercial building. And we have a projection that distributed utility of tomorrow is more divided into several things, such as a power plant. Nah, and here I would like to discuss about how is the future of power plant, especially in renewable energy. Does it have a potential in viewers, and how it implicates in Malaysia? Because in Indonesia, here we lead to a new renewable energy system. So the power plant is we are focusing in a solar system.
Okay.
So I would like to compare between Indonesia and Malaysia.
And
So
Malaysia.
thank you.
Okay. Very interesting question. Yes, currently there is a lot of trend on an increasing of DG, distributed generation. I think it's the same anywhere around the world. You have DG. The only different now would be what would be the different type of DG that you have. Now that depends on what the country has or what the technology that the country has. I think similar here, typical DG would be solar panels, solar PVs. Solar heating is very seldom being used because you need a bigger space. So let's say we talk about solar PV. So solar PV talks about the sun hitting the solar panel. Then the solar panel will convert the sun rays into energy, and then that energy is being transmitted into the distribution grid through your converters, which is DC converted to AC. Now, the concept of solar PV is very nice. It's green. There's no emission. Well, theoretically, there's no emission. However, of course, some may argue manufacturing solar panels create emission. So that should also be taken into account. But okay, we put that point aside. So we focus back into PV. As I mentioned before, the main issue on PV would be the sun. If you have sun, you have energy. So the minute the sun intensity reduces, your energy output will reduce. Okay, so let's say if I have a cloud cover over my solar panel, then my power output will also drop. If suddenly it's raining, my power output will also drop. Let's say if I don't wash the solar panel, I have dust accumulation, the solar PV performance will also drop. Now, if you talk about dust, that is something that we can control. We just need to wash it, make sure it's clean. But you cannot control cloud. You cannot tell the cloud, don't go here, go elsewhere. You cannot do that. You cannot tell the rain, don't rain now, rain later. You cannot even tell the sun, don't go down yet. You need to shine even at 8 o'clock at night. You cannot do that. So therefore, the main problem with solar PV is that you can only get power when there is sun. Now, it looks very simple, but it can give a problem to utility. Because if you remember the load profile that I showed, let me share that load profile again. Okay. Let's say, for example, I'm over here. So this is, let's say, at 1 o'clock tengah hari, pukul 1 tengah hari, pukul 1 tengah hari. By right, it is supposed to be nice and hot and the sun should be shining. And that is where I have the peak load. So basically, my solar PV should be able to help that. But what if suddenly, due to that season of the year or that month, suddenly there's sun, but then there's a lot of cloud. So therefore, your PV cannot produce as much. Or maybe during this tengah hari ni, it rains. So your output drops down to 0, for example. So for a utility, that will create a problem. Because if I don't know my weather well, I will be caught off guard, which means suddenly there's no power from my PV plant. Then my frequency will start to drop because not enough generation. Then maybe my voltage starts to fluctuate because I don't have good control of my grid. So I have to have generator on standby to be online and so forth. So the tricky part is when I have solar panels connected, I have to be ready for these contingencies. The same thing, if you go to Europe, they use a lot of wind farms. They have a problem. Maybe during peak load, suddenly no wind. So the solar farm will not function. Then you lose power. Then you have problems. So they need to coordinate that to make sure that um, the power will be there when you require. For example, another problem with wind. Sometimes during peak load, they have no wind. When there's no load, you have a lot of wind. So what do you do with the excess energy? So then that's where energy storage comes in, so that maybe you can store the energy first, then inject it back later. So those are some of the few things that you need to take into account. Now, coordinating this DG is tricky. So that's why they look into the concept of smart grid. Now, smart grid currently, I can tell you for sure, has not been fully implemented 100% around the world, not yet. But it's a concept that a lot of countries are considering. Technology-wise, it talks about coordinating energy automatically. You don't need people to manage it. It will actually manage it for you. And you also give empowerment to the customer to say that I want to buy power from solar, I don't want to buy power from coal-fired power plant, for example. So smart grid will help to coordinate that. However, that is just the technology. In order for you to implement technology, the other part must be ready. Your standards, your policies, your rules and regulation must be ready. So in Malaysia, yes, we are considering a lot on PV because we have a lot of PV panels. I think the government is pushing a lot on renewables. So we have PV, one. Second, they are also pushing more on biomass, which is from sewer. From sewer systems, I can extract methane and get energy from there, biomass. And also, I think similar to Indonesia, you have a lot of palm oil, palm trees, right? Palm oil trees. So therefore, the empty fruit bunch, the byproduct of the palm oil can be reprocessed for biomass as well. So that is also another option. Another one that is a possibility in the future is hydrogen, where you use power to extract hydrogen from water and use that hydrogen to power to get your energy for going by using fuel cell and whatnot. So that is not commercial yet, but that is something that people are testing. In Japan, they have that already in their labs. I think now you also talk about hydrogen powered car. So that is something to consider in the near future. Okay, so I hope I've covered that. How about in Indonesia? Are you more focused on PV or you have more than just PV?
Basically in Indonesia, we're starting from PV. If we can each household, if they can produce a PV, so it will be help our electricity company here to provide and distribute about the distribution. And after that, we are now starting to use kind of electrical vehicle. So electric vehicle is like big campaign in our country to reduce the zero emission carbon. And in each province in Indonesia is actually the government have a program to have a natural power plant. So based on that, we can see how and what is the natural resources that can be used for power plant, such as in my province in Banten. Actually, our geographical things is near with ocean, so we have a power plant that stimulate by the water. And maybe in several provinces in Indonesia, they have a power plant supply with wind. So we started to lead an um like zero emission carbon. That's our main campaign here. So, sir, I would like to give a point here that natural resources is has advantages and disadvantages, right? It depends on the weather. Correct me if I'm wrong.
Yep, true. I think what you have now is good, but of course, let's say for example, you want to introduce electric vehicle. concept-wise, emission-wise, is very good. But I'm sure if you ask the network planner, they will have headache. Because EV cars will have to take into account the network strength when the
Yes.
car is actually charging. And that may cause stress to the network. And usually, I'm sure network planners, they don't like too much change because more work for them to think about, right? So you need to figure out what to upgrade, what to make sure that the network can handle EV cars. But regardless, I think it's is the right direction. I think even in Malaysia, people are now starting to relook back at EV cars. We have just started having EV cars, but it's not a lot. But what our Energy Commission says that we have EV cars, you have to, the utility have to manage the network. It has to be ready to manage it. So like I think we have similar issues for us to consider. The network has to be ready technically, and the next part will be the user. I don't know about fuel price in Indonesia. In Malaysia, the fuel price is cheaper, so therefore the push to use EV is less, because if they calculate, it's cheaper to use normal car because our fuel are actually subsidized by the government. But if
Oh,
I
I
go to
see.
the US, where the fuel price is market, is more expensive, then maybe using EV is better. So it has a lot of factors. It's not just about using EV, but you need to make sure that the market or the economy is suitable. But it's a good move. Everybody should try it so that we can learn how to manage it in our own way. Every country has a different way because it depends on the country.
Okay, thank
Okay.
you, Miss Profita, for the question and insight. And thank you, Prof. Izam, for the answer.
You're
Uh,
welcome. Thank you.
Okay, dear ladies and gentlemen, because of time limitation, we are already in the end of the course. Maybe your lecturer from ATPLN will give you an assignment to summarize our course today. So please be ready. I think I think because before we close, we should have a photo session. To all students, please enable the camera and also use the virtual background that we have given. We will do a group photo session starting from first screen. Okay.
Wow, Prof. Ramesh, you're still around.
We ready? 1, 2, 3. Okay. Okay, thank you.
Dr. G is also around here.
Yeah. Okay. I just put the link attendance in the chat room. So for our student, please check and fill the form. Prof. Izam, would you like to send the presentation material to us later?
Yes, I will share the presentation. Maybe by tomorrow, I'll pass it to you.
Okay.
Okay.
Thanks before, Prof.
Okay.
Okay, ladies and
But
gentlemen,
if
it
there are
doesn't. Yeah.
also other questions, they can also email me. I think my presentation slide, there's an email address. Then they can
Okay.
also email me if they want to ask anything later.
Okay, thanks a lot, Prof.
All right.
Okay, ladies and gentlemen, it doesn't feel like we are in the end of the course. I would like to thank Prof. Izam and Unitan team, Ms. Nur Aziza, Prof. Rames, and also the entire committee on duty, Mr. Adri, Mr. Tony Kurniawan, Ms. Dia, and students who have participated this lecture well. Hopefully this course in this evening can be beneficial to all of us. Finally, as MC, I apologize if there are mistakes on me. Hopefully we can meet again in another opportunity. Finally, I say goodbye and wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam.
Waalaikumsalam
Thank
warahmatullahi
you.
wabarakatuh. Thank you very
Thank you,
much.
Prof. Rames, Prof.
Okay, no
Izam.
problem. Great lecture.
Okay.
Izam.
Thank
Good
you.
lecture.
Thank you.
Thank you, everyone.
Thank you, everyone.